Hi everyone, welcome back to Dave's Math channel. I'm your host David Tare, and this is my third video in my sub-series of applications of derivatives on my series on first year calculus. And today I'm going to talk about the optimal shape of a cylindrical can, i.e. the shape that a cylindrical can should have that minimizes its surface area for a fixed volume. So let's begin. So here's the problem, just written out in full. So suppose we want to make a cylindrical can with a given volume V, as shown on the right. What should its radius R and its height H be in order to ensure that its surface area S is minimal? Let's set this up. So first we want to come up with formulas for the volume and the surface area, and I think you guys all learned these probably in grade school or maybe high school. So you know that the volume of a cylinder is pi r squared h, and you know the surface area, it consists of two end caps, each with area pi r squared. So their total area is 2 pi r squared, and the surface area of the curved portion is 2 pi rh. So these are the formulas. But now what we want to do is we want to minimize the surface area S while keeping the volume V constant. So what we can do to do that, we want to eliminate one of the variables too, because we're only working with univariate functions. We haven't learned multivariate calculus yet. That's usually not taught until second year calculus. That is another way to do this problem, but we want to stick to one variable. So what we do is we solve for h, the height, in terms of the radius, using the volume as a constant. So you can just invert the formula for the first formula for the volume, solve for h. You get h equals v over pi r squared. Now you can use that formula to substitute for h in the second formula for s, and now we get a function of r. So when you do that, you get s of r equals 2 pi r squared plus 2v over r. Well, that's nice, because now we have a differentiable function of r that we want to minimize. So we just do it. We calculate the derivative, because that's how you minimize or maximize a differentiable function. So we have s prime of r equals 4 pi r minus 2v over r squared. And we want to set that equal to 0, so that means we have 4 pi r equals 2v over r squared. And if you solve for r, you get r equals v over 2 pi to the power 1/3. I like to write fractional powers this way instead of using radicals. I mean, some people write this as the cube root of v over 2 pi, but I just don't like using cube root symbols. It's more complicated, at least in my mind it is. Because roots, radicals are, is they're just fractional powers. So you might as well write it as one. So that's our formula for R. And we can also solve for h in the same way. We know that h is v over pi r squared. We can plug in the equation we just obtained for r. And when we do that, when we simplify everything, we find that the height is equal to 2r. It's twice the radius. And that's a nice result. So what that says is no matter what the volume of the can is, as long as it's a cylindrical can and we want to keep that volume fixed, the way we should design our can is to make sure that the height of the can is equal to twice its radius, or if you like, equal to its diameter. That means that vertical cross section of the can would look like a square. Kind of a nice result. And you've probably seen this, like when you go grocery shopping, a lot of the things you have to buy are in cans, right? Soup, or maybe tomato sauce or whatever, olives. Well, just think about cans, not bottles. But if it was a can where the cost of the surface, every part of the surface was the same cost per unit surface area, then we would have a can that's shaped this way. It would have the same height as its diameter. Most cans, I think soup cans, the height is a little bit bigger than the diameter, And I think the reason that's the case is because the end caps are actually more expensive per unit surface area than the cylindrical portion. And that kind of makes sense because a soup can has a little, it has a little opener on top, so you would expect that that would make it more expensive. That end cap, at least, more expensive than the rest of the can. And there's probably other reasons too. Usually the bottom of the can is a little thicker than the sides, But yeah, if you wanted to analyze it in terms of cost, this would be another calculus problem. You'd have to come up with a formula for the cost of the can. You could do this. You could probably do a problem like that. I didn't pick one here, but you kind of get the idea. At least, but for this simple example, the answer you get is that the height should be equal to the diameter. Anyway, that concludes my video. Thank you for watching. Long live math, and I'll see you guys next time.